Today's lecture is about how one may do inference within the M-estimation framework. So this lecture is the third in a sequence of lectures on nonlinear estimation, where we've previously introduced the M-estimation framework, in part through our example of nonlinear least squares. And in the last lecture, we talked about various asymptotic properties of M-estimators and how one may establish them. This lecture is about how one may build on these asymptotic properties in order to do inference. The next lecture will be on maximum likelihood estimation, which constitutes a particular instance of M-estimation. To recap, the setting that we're studying is one where our object of interest, this parameter, what we may think of as the true theta, is the solution to a population minimization problem. The population, we're minimizing the expectation over some function q, which depends on observables w, which may be, say, outcomes and explanatory variables. And we're minimizing over various candidates parameters theta as captured by this parameter space, capital theta. Our M-estimator arises from the analogy principle by replacing the population expectation by the sample average, which you can obtain from the data. And M-estimator is then any solution to the resulting sample problem. Now in the last lecture, that is lecture 7, we established that under a certain set of conditions, one may show that the sequence of M-estimators is root n asymptotically normal. That is, the M-estimator centered at the true parameters and then scaled by the square root of the sample size converges in distribution to a normal with zero mean and variance of a sandwich form. The main goal of this lecture is to obtain methods or establish methods for estimating this asymptotic variance in a consistent manner. So the outline for the rest of this lecture goes as follows. We'll spend the bulk of the lecture talking about exactly this problem, which will lead more generally to doing valid inference. And then we'll use our working example of nonlinear regression and the nonlinear least squares estimator to illustrate the points as we go along. Then we'll extend the framework to a multivariate nonlinear regression setting, which will lead to a multivariate extension of the nonlinear least squares estimator. This will allow us to recover our earlier results for estimators designed to consistently estimate the parameters of the linear unobserved effects model for panel data. We'll also talk about how one may use consistent variance estimators in connection to hypothesis testing, specifically testing nonlinear parameter restrictions. And then I'll end the talk by discussing various criteria that one may consider or employ in choosing among candidate estimators. First up is our main goal for today, which is developing methods for valid inference within the M-estimation framework. So recall here that if we've established a result of asymptotic normality for the M-estimator, here theta hat, then the asymptotic variance of the M-estimator is given by a sandwich form upon dividing by the sample size n. Here there are two components to the variance, A0 and B0, or two contributions to the variance, I should say. The first contribution, or the bread component, A0, takes the form of the expectation of a Hessian, where here the Hessian is with respect to the q function it's the second order derivative or Hessian of the Q function with respect to theta. And it is evaluated at the true parameters, theta naught. The B component, or the meat of the sandwich, if you will, takes the form of an expectation over the outer product of the scores. The scores being defined as the vector of partial derivatives, also of the Q function, with respect to theta. And again, these scores are evaluated at the true parameter. So if we seek an answer to the question, how may one consistently estimate the asymptotic variance, it boils down to the question of how may one consistently estimate the variance components A0 and B0. Now there are, in principle, many approaches to obtaining consistent estimation or consistent estimators, depending on the assumptions that one is willing to make or the structure that is available to us from the problem. So in the next couple of slides, I'll go through 3 different approaches and discuss their various benefits as well as their drawbacks. First up, that is our first estimator, is what we may think of as the most structural approach. That is the approach relying on the most assumptions. So this approach to obtaining a consistent estimator relies on the following idea. Suppose that we were able to analytically solve for the expectations involved in expressing A0 and B0. Then we could think of the A0 matrix and B0 matrix as arising from functions, let's call them A and B as well, evaluated at theta naught, the true parameter. Now, if we had such analytic expressions available, that is, we are able to actually solve for these expressions or expectations, then we could simply replace the unknown parameter, or true parameter theta naught, with our consistent estimator thereof. As long as these two vector, or rather matrix functions, A and B, are sufficiently smooth in the parameter, then the resulting estimators will be consistent for A0 and B0. So that's one idea, or one possible way we could come up with an estimator for the various asymptotic variance components. Now this estimator, or this idea, clearly has some drawbacks. One is that we need to analytically solve for these expectations. Now, in general, in order to solve for these expectations, we would have to completely specify the distribution of W. This may or may not be something that we're willing to do. For example, often we're thinking of W as being composed by 2 parts, some outcomes and some inputs, and we've only specified, say, the distribution of the outcomes given the regressors X, not the distribution of the regressors themselves. Hence, this joint distribution of Y and X, that is, the distribution of W, may simply not be available. Or it may not be something that we are willing to take a stand on. Moreover, even if we do have such an expression, if our model does allow us to solve these expectations in principle, obtaining closed form expressions is in general very difficult and prone to error. For these reasons, this first estimator, the most structural estimator that we'll consider, is rarely an option in practice. The next estimator that we'll consider is in some sense the least structural. This estimator builds on the observation that both A0 and B0 arise from expectations of functions of theta naught. Since these variance components arise as expectations, we could simply think about invoking the analogy principle. The analogy principle here would involve two steps, or one may think of it as involving two steps. First up, we replace the population expectations with the sample averages. And then we replace the unknown true parameter with our estimator thereof. The resulting estimators of the variance components take the following expressions, with the following forms. Our estimator of A naught is the average of our estimates of Hessian contributions, where the Hessian contribution, here hi hat, is our Hessian function evaluated at the ith observation and the M-Estimator. Our estimator for B naught, call it B hat, arises from the average of the outer product of our estimates of the score contributions. Here the score contributions, or our estimates thereof, arise from evaluating the score function at the ith observation and the M-Estimator. Now one may show that these estimators, A hat and B hat, are consistent for their population counterparts, A naught and B naught, under very mild additional conditions, which for brevity I here skip. In this sense, these are good estimators. Let's discuss this second type of estimator, the least structural type of estimator, in a bit more detail. So here I'm just copying our previous expressions for easy reference. Now, since these now under our previous assumption of twice continuous differentiability of the Q function with respect to theta, we can always calculate Hessians and scores. So for this reason, these estimators are essentially always available under our previous assumptions. Moreover, by definition of the M-Estimator as a solution to the sample problem, we know that the Hessian of the sample objective must be positive semi-definite, which means that A hat, which is the Hessian at the M-Estimator, is at least positive semi-definite, which is a plus. The drawback here is that in order to compute A hat, we need to compute Hessians. That is, we need to calculate second-order derivatives of the Q function with respect to theta, which may be complicated if the Q function's dependence on theta is complicated. Or if we leave this calculation to the computer, it may be a heavy calculation for the computer to carry out if the Hessian matrix is somewhat large. A special case arises when Q is strictly convex in theta. In that case, the resulting Hessian contributions are positive definite matrices, no matter what theta we look at, and hence their average will also be positive definite. As a result, the resulting A estimate, or A naught estimate, will not only be positive semi-definite, but actually positive definite. But this, of course, this case where Q is strictly convex in all elements of theta is a very special case. Having discussed estimators 1 and 2, which were in some sense the most structural and least structural approaches one could think of, we next move to an approach which lies somewhere in between. For that reason, we'll refer to this third estimator as the semi-structural approach, or leading to a semi-structural estimate. So what's this additional structure that we'll impose. At this point, we'll assume that W can be separated into two parts, Y and X, where we think of Y as being the outcomes and X the regressors or conditioning variables. Now suppose that theta naught, our parameters of interest, index some feature of the conditional distribution of Y given X. This feature could be the conditional mean or conditional median, or it could be just the entire conditional distribution. Now, if we've made this division of W, then we may think of W into two parts. Then we may think of calculating conditional expectations, conditional with respect to X. We may therefore define the conditional expectation of the Hessian, that is the expectation over Y for given X of the Hessian. Define it to, or we may give it some name, let's call it A. Now this A will depend on X, the value of the conditioning variable, and also theta naught through the dependence of theta naught inside the Hessian. Now, an alternative estimator of A naught arises as follows. We take the average over the contributions or our estimates of the conditional Hessian contributions, here denoted by AI hat. Now AI hat, our estimate of the conditional Hessian contribution, arises from evaluating the A function at xi and replacing the true parameters with our M-Estimator. Again, let's discuss this option in a bit more detail. So here I've again carried through our definition of this alternative A naught estimator from the previous slide. Now it turns out that under some mild assumptions, this estimator is usually positive definite in the sample, which is of course a major plus since we're trying to invert it. However, this is only a useful approach if we have some way of obtaining the A function, or to be specific, the conditional expectation of the Hessian in closed form. Or at least we should be able to obtain some approximation thereof in an easy manner. And now we see the drawbacks of this method, in that it relies on more structure, right? It relies on us knowing this stuff and us being right in our calculation of this stuff, which of course could lead to errors. A similar type of critique could be directed at the fully structural approach, or what we call the most structural approach earlier. Having discussed these various variance estimators, I here list the resulting asymptotic variance estimators. If we apply the least structural approach, which is essentially always available given our previous assumptions, then the resulting estimator of the asymptotic variance of our M-Estimator follows from replacing A naught with our estimator thereof and B naught with our estimator thereof. The resulting expression, or the expression that results from this substitution, is highlighted here in the box. We see that what we really need to calculate is the sum of our estimates of Hessian contributions and the sum of our estimated products of scores. So these calculations, one may think of carrying them out in practice using the computer. When using the semi-structural approach, we use the same estimator of B naught, the meat part of the asymptotic variance, but now we're replacing our earlier A-estimator with the semi-structural one. That is, the approach that relies on slightly more structure. The resulting asymptotic variance estimator takes this form. Now we need to calculate not the sum of the estimated Hessian contributions, but the sum of the estimated conditional Hessian contributions. Now one may show that under slightly stronger assumptions or somewhat mild additional assumptions, the least structural approach leads to an estimator which is fully robust. That is, it leads to a consistent variance estimator without essentially more assumptions that we've already made. The semi-structural approach leads to an asymptotic variance estimator which is consistent at least under the additional structure that we've imposed in constructing it. For this reason, we might refer to it and will refer to it as a semi-robust variance estimator. So these constructions are all nice and dandy, but they're somewhat abstract. So let's now go to an example in order to illustrate the necessary calculations that one would have to carry out in a simpler setting. And for that purpose, let's go back to our friend, the nonlinear least squares estimator. So recall that in the nonlinear regression framework and the nonlinear least squares estimator is an M-Estimator which uses the following Q function. That is, we use the square of the difference between the outcome of interest and our model for its conditional mean, as represented by this M function. Now, provided that M, viewed as a function of theta, is sufficiently smooth, that is, twice continuously differentiable, we may make use of the chain and product rules for differentiation in order to derive the nonlinear least squares score and Hessian. The score expression that arises from differentiation is given by this expression in the box. It's -2 times the difference between the outcome and our model for its conditional mean times the gradient of the M function with respect to theta. Or I should say the column vector of partial derivatives of M with respect to theta. If we differentiate the nonlinear least squares score, we get the nonlinear least squares Hessian. So this is where we need both the product and chain rules. The resulting expression is given here. Now we have both a term that involves the outer product of the derivatives of the M function, as well as a term that involves the second order derivative of the M function. Now, before diving into further calculations, let me just stress that our nonlinear regression model doesn't specify, is not a model for the entire conditional distribution of y given x. Only one feature, its conditional mean. For this reason, the fully structural approach is in this example not possible, and I won't mention it further. Next up, we'll think about how to construct a consistent variance estimator for the nonlinear least squares estimator. First, let's think about how we may estimate the meat of the nonlinear least squares estimator, that is, the B0 matrix. First, what's the structure of this matrix? Well, if we evaluate the score function at the true parameter, and recall that our notation U is short for y minus our model for its conditional mean at the true parameter, hence the score is just 2 times U, or minus 2 times U, times the derivative of the M function with respect to theta, and then evaluated at the truth. If we take the outer product of these scores and then compute the expectation over the data, or both y and x, then we arrive at b. B is then just 4 times the expectation of the square of u and the outer product of the derivatives of m with respect to theta, and evaluate it at the truth. Now let's introduce a bit of notation. Let ui hat denote the nonlinearly squares residuals. And let's substitute in the nonlinearly squares estimator in place of the true parameter in the derivative, or in this case, the gradient of the m function. Then we may estimate the ith gradient contribution and give it a name, here abbreviated by this large hat of the gradient of m with respect to theta for the ith individual. The resulting b estimator is then 4 times the average of our square of the nonlinearly squares residuals and the product of the score contributions, or rather our estimators thereof. Having constructed an estimate of the meat component of the asymptotic variance, we next move on to discussing how one may estimate the bread component. That is, how one may construct an estimate, or consistent estimate, of A0. Now we look at the Hessian, which is involved in A0, and evaluate it at the true parameter. Then we may express the Hessian of the Q function involved in nonlinearly squares as 2 times the outer product of the derivatives of m minus 2 times u times the Hessian of m. All of these expressions being evaluated at the true parameter. Now, we already have estimates and notation for the first component, or the first part of the Hessian. And we already have notation for the nonlinearly squares residuals, which estimate these u's. Hence, all we need is an estimate for the last part. So let's look at the ith contribution to this Hessian, or rather the Hessian of m, which enters the Hessian of q. And substituting in our M-Estimator in place of the true parameter, we may estimate the ith Hessian contribution, or M Hessian contribution, and give it a name, which is what I use this seemingly complicated notation with a wide hat for. Then our least structural approach for obtaining an estimator of A0 yields the following estimator. It is the average of our estimates of the Hessian contribution, where our estimate of the ith Hessian contribution is 2 times the outer product of our gradients, or estimates of the gradient of m for the ith individual, which are intended to estimate this part, minus 2 times the nonlinearly squares residuals, multiplied by our estimate of the ith M Hessian contribution. The fully robust estimator for nonlinearly squares then follows from substituting in this A hat and the B hat from our previous slide. Now that we know how to obtain a fully robust estimator of the asymptotic variance of the nonlinearly squares estimator, let's take a look at how one may obtain a semi-robust estimator. Again, so we're still thinking about how one may estimate A0 in the context of nonlinearly squares. And here I've repeated the expression for the Hessian function at the true parameters from our earlier slide. Now we may notice that the last part of this Hessian expression involves a product of a function and u. Now this function here, which is the Hessian of m, depends on x alone. Hence, if we condition on x, we may treat it as a constant. I mentioned this because if the model is well specified, then u has conditional mean 0, where we are conditioning on x. For this reason, if we're assuming the model is well specified, that's the additional structure, then a, the conditional mean of the Hessian, where we condition on x, simplifies and is given by the first part of the Hessian alone. Here, the second part drops out because the conditional mean of u given x is 0. Hence, the semi-structural approach to estimation of A0 yields an estimator, A tilde, which is an average over estimates of the ith conditional Hessian contribution, which is simply given, is here given by 2 times our earlier estimates of the gradient of m for the ith individual. Using this in place of A0 and our earlier estimator of B0, we can construct a semi-robust estimator of the asymptotic variance of the nonlinear least squares estimator. Let's discuss this semi-robust estimator in a bit more detail. So here I've just taken our earlier estimates and substituted them into our formula in order to express everything on one line. We see that the semi-robust variance estimator in nonlinear least squares hinges on the sum of some gradient contributions, or their product, and the sum of gradient contributions, or their product, upon multiplication with the square of the nonlinear least squares residuals. Note here that in deriving this estimator, we've only used that the model is well specified. We haven't actually placed any restrictions on other features of the distribution of y given x. In particular, we haven't placed any features of the conditional variance of y given x. For this reason, this estimator, the semi-robust estimator, is sometimes referred to as a heteroscedasticity robust variance estimator for nonlinear least squares. So you may see this type of language if you use nonlinear least squares and some standard software package. Now, if we want to obtain asymptotic standard errors using the robust or semi-robust estimator, we would simply use the square root of the diagonal as usual. Let's continue our discussion of the semi-robust variance estimator of the nonlinear least squares estimator by discussing a couple of special cases. So again, I've just carried through the long but manageable estimator of the asymptotic variance of nonlinear least squares. Now let's suppose that we invoke or make use of an exponential regression function. That is, in place of m, we use the exponential function of the inner product of x and theta. In that case, differentiation is straightforward. Using the chain rule, we can calculate the gradient of m with respect to theta at the true parameter as the exponential function of the inner product of x and the true parameter multiplied by x. Evaluated at xi and replacing the true parameter by our nonlinear least squares estimator, we can therefore easily construct an estimate of the outer product of the gradients. And the result is the exponential function to 2 times the inner product of xi and the nonlinearly squares estimator multiplied by the outer product of the regressors for individual I. So we know how to construct the bread components. The only thing missing in order to construct the meat component here is to plug in the nonlinearly squares residuals and square them. In another special case, we can recover a dear old friend. So let's look at our earlier focus point, which is the linear regression model. The linear regression model arises from the nonlinear case by replacing the m function with the inner product of x and theta. In this case, the gradient of m with respect to theta is just x, no matter the point of evaluation. And in particular, it's equal to x for the true parameter. Hence, an estimator of the outer product of the gradients is especially easy to construct since we can just plug in the data. There's no need for estimation. So in this particular case, we know how to construct estimates of the outer product of the gradients. And in order to construct residuals, we simply use the OLS residuals. The resulting estimator, if you plug in all these components and write it out, we see that the resulting estimator is simply the usual heteroscedasticity robust variance estimator for the least squares estimator. So our earlier framework, or current framework, allowed us to recover the robust heteroscedasticity robust variance estimator for least squares as a special case. Next, we extend our nonlinear regression framework from an earlier lecture to allow for a multivariate outcome, which will then lead us to consider a multivariate extension of the nonlinear least squares estimation method. So now what's new is that we allow for an outcome y, which is possibly vector. Here its dimensions are denoted by g by 1. We're still interested in a regression model, that is, we're interested in modeling the conditional mean of y given some conditioning variables x. And as our model, we use the vector function m, which depends on x and theta as before. The only thing different is that it is a vector. Now, the multivariate nonlinear least squares estimator arises from using the M-estimation framework with q function equal to the sum of the squares of differences between the gth outcome and our model for its conditional mean. We may also write this in vector notation, which makes things a bit more compact. Now this sum of squares is simply the norm, or the square of the norm, between the vector y and our model for its conditional mean. Now since the multivariate nonlinear least squares estimator is a special case of an M-estimator, we could think about invoking our earlier theorems in an attempt to establish, say, consistency, as well as asymptotic normality, as well as consistent estimation of the resulting asymptotic variance matrix. So that's the idea. Now in order to get at a form of our estimator of the asymptotic variance matrix, let's introduce again as shorthand u, which is short for the difference between y and our conditional mean, or our model for its conditional mean, at the true parameter. Then, assuming correct specification, the components entering the asymptotic variance of the multivariate nonlinear least squares estimator are A0 and B0, which have the following expressions. Again, we have an expression involving some outer product of a derivative. The derivative, a relevant derivative here, is now the Jacobian of M with respect to theta at the true parameter. So this here, I should mention, since M is G by 1, this is a G by P matrix, so its transpose is P by G. So again, the resulting matrix is P by P. When it comes to B, the meat of the asymptotic variance, it is also similar to what we've encountered before for nonlinear least squares. It involves this Jacobian term, and then the square of U, where the square is now in a vector sense, hence the outer product. Now, given these expressions for the variance components, we could think about going through the same steps as before in order to discuss consistent methods for obtaining consistent estimators thereof. All I'll say at this point is that robust estimation or semi-robust estimation is completely analogous to the scalar case. So I'm going to skip a deeper discussion here. I do want to point out, though, that there's a difference in the meaning of robust. Since we're now dealing with a vector outcome, robustness is not only understood in terms of robust to heteroscedasticity, but also robust to cross-equation correlation. So these expressions give us an idea of the structure of nonlinear least squares, or the asymptotic variance of the nonlinear least squares estimator in the multivariate setting. Now let's make these expressions a bit more recognizable by considering an example. Namely, let's go back to our earlier focus point, which was the linear unobserved effects model for panel data. Now let's consider the model, the linear panel model from earlier in the course, assuming that the regressors are strictly exogenous. Now we still, in order to control the individual effect, let's for now just compute first differences and stack over the remaining capital T minus 1 periods in order to obtain this equation system. Now, under our assumption of strict exogeneity, delta ui, the vector delta ui, given regressors in all time periods, is equal to 0. That is, we have the conditional mean of the error, if you will, of this equation in differences is equal to 0. In other words, the conditional mean of the outcome differences is linear in parameters beta naught. Now, for this reason, this setting here is a special case in which we may want, which is ideal for using the multivariate extension to nonlinear least squares that we just discussed. So let's look at the particular form of the asymptotic variance matrix for the multivariate nonlinear least squares estimator in this case. Now here, our M function was delta xi, theta, or beta if you will. So if we want to differentiate with respect to theta, which is what we do when we calculate the Jacobian of M, all we get is delta xi. Now this Jacobian doesn't depend on the parameters anymore due to linearity. Hence, we may replace it in our variance formulas, or we may simply plug it in our variance formulas in order to construct an estimate of the breadth component. We may similarly use the multivariate nonlinearly squares residuals in place of the u's to construct an estimator of the meat component, b naught. And the resulting estimator is given in this display equation. Now this estimator is a robust variance estimator, or semi-robust if you will, since we're assuming a correctly specified model. And if you spend a moment staring at this, you'll recognize that this is exactly what we earlier called the robust estimator of the asymptotic variance of our first difference estimator. Hence, we recover our earlier setting for the first difference estimation method. Now we know that, note here that robust in this current setting means robust to both heteroscedasticity and serial correlation. So here serial correlation plays the role of cross-equation correlation. One may similarly look at the fixed effects estimator and show that it can be embedded in the current framework. And I highly encourage you guys to go through that example on your own in order to check that you understand the various steps involved. So our discussion here of how one may obtain a consistent estimator of the asymptotic variance matrix is useful for deriving standard errors of the estimates, say. But it may also be used in a more general context of hypothesis testing. So that's what we'll discuss next. Suppose now that what we want to do, what we want to test, are Q possibly nonlinear restrictions. So we want to test the hypothesis, the null hypothesis, say, H0, that some function of the true parameters, theta naught, is equal to 0. So here, the possibly nonlinear restrictions are described by this restriction function C. So here C is a function from our P to our Q. Now what type of example or what type of hypothesis may we entertain within this framework? Well, we may, for example, entertain the hypothesis that the first element of the true parameter is equal to the square of the second, which in our current framework may be expressed as the function C given by the first element minus the square of the second when evaluated at the truth is equal to 0. Another possible hypothesis of interest is that the product of two coefficients, say the first two, is equal to 1 or some other constant. In that case, in order to express this hypothesis in our current framework, we would choose a C function which takes the product of the first two elements of C and subtracts 1. But these are just examples. This framework is much richer than what these examples illustrate. So our interest lies in testing the null hypothesis that C of theta naught is equal to 0. That is, we're interested in testing these Q possibly nonlinear restrictions. Now let's suppose that for the purpose of carrying out this test, we have access to some estimator, say theta hat, which is root n asymptotically normal. For example, this could be an M-Estimator. provided the true parameter theta naught can be framed as needed to fit inside the M-estimation framework. But at this point, we don't need it to be an M-estimator, we just need it to be rooted and asymptotically normal. Now let's suppose also that we have some consistent estimator of its asymptotic variance at hand. If so, then we have all the necessary ingredients in order to construct a wall statistic, or to be specific, a wall statistic for the possibly nonlinear hypothesis listed up here. This wall statistic is given by the following quadratic form, where we use as the sandwich components our restriction function upon replacing the true parameters by our estimates thereof. The meat entering the wall statistic itself involves a quadratic form. It is the inverse of a quadratic form. And here the bread components inside this inverse is given by the Jacobian of the restrictions evaluated at the parameter estimate. And the meat component is our consistent estimator of the asymptotic variance. Now, under the null hypothesis and some additional mild conditions, one may show that the wall statistic converges in distribution to a chi-square distribution with q degrees of freedom. Hence, under the null hypothesis, the limiting distribution of the wall statistic is completely known. It's something we can look up in a table. The wall test then arises from the following decision, or this following decision rule. Let alpha denote the significance level, for example, 5% or 10%. Then we reject the null hypothesis, that is, we reject these nonlinear restrictions, if and only if our wall statistic exceeds the 1 minus alpha quantile of a chi-square distribution with q degrees of freedom. Now in this testing procedure, there are a couple of implicit assumptions. For example, the procedure itself presumes that our testing or our restriction function c is continuously differentiable, as differentiability is required in order to compute a Jacobian. It also presumes, at least implicitly, requires that the Jacobian of the restrictions at the true parameter is a matrix of full rank. Recall that this Jacobian is Q by P, and Q is taken smaller than P, so it can have at most rank Q. Now let's go back to our earlier examples to see whether or not this is actually something to worry about. Starting with our first example, where we're interested in testing the hypothesis that the first element of the true parameter is equal to the square of the second. In that case, if we differentiate the restriction function with respect to theta, we get 1. Well, with respect to theta 1, we get 1. And with respect to theta 2, we get minus 2 theta 2. Hence, the relevant Jacobian is given by this 1 by 2 matrix, or row vector, which has 1 as one of the elements. Now, this matrix can at most have rank 1, and since it doesn't have a 0 row, since it's not equal to the 0 matrix, it is in fact of rank 1. So for this particular hypothesis, the second requirement is satisfied. What about the other hypothesis that we looked at a moment ago? This hypothesis stated that the product of the two first elements of the true parameter was equal to 1. Now, if we calculate the Jacobian of this function, we have to differentiate first with respect to theta 1, which yields theta 2, and with respect to theta 2, which yields theta 1. So the relevant Jacobian is this 1 by 2 matrix, which involves the second component of the true parameter and the first component of the true parameter. Now, it is actually possible for this matrix to have no rank. That is, it's possible for this matrix to fall short of its maximum rank, which is 1. In particular, if these two elements are both 0, then the rank of this matrix is 0. So in this case, our testing framework rules out the possibility that both of the first two elements of the true parameter is equal to 0. Now, we've spent some time here in the last 3 lectures. We've spent some time talking about methods for obtaining a consistent estimator or establishing that an estimator is consistent, as well as square root n asymptotically normal, and also how one may consistently estimate the resulting asymptotic variance matrix. We next provide a couple of criteria, or some criteria, for choosing among different estimators. Now, the problem here is that in principle, there are infinitely many Q functions that one could think about using, thus leading to possibly infinitely many M-Estimators. So how does one choose the Q function and therefore the resulting estimator? Now, the econometrics literature has suggested a number of criteria, and here we'll go through some of them. The first criteria is that the resulting M-Estimator, the resulting estimator, should be consistent for what we're trying to estimate, that is, our parameters of interest. In our M-estimation framework, the requirement of consistency subsumes our requirement of identification. That is, the true parameter should not only be a minimizer of the population criterion, but it should be the unique solution to this population problem. Consistency means that in the limit, the distribution of the estimator collapses on the estimate, what we're trying to estimate. In this sense, consistency, or for this reason, consistency is really a minimal requirement. Next, suppose that we have two estimators to choose between, and suppose that both of them are consistent. Then ideally, one should choose the estimator which converges the fastest. That is, the rate of convergence to the true parameter should be as fast as possible. So here I've tried to illustrate this in a graph or in a figure where we look at two particular instances or realizations of our parameter paths for estimator 1 and estimator 2. And we see that estimator 1 for this particular realization converges faster to the true parameter than estimator 2. Now, why would we want to choose an estimator with a fast rate of convergence? Well, the reason is that we need less data in order to obtain the same level of precision. So in that sense, one estimator is preferable compared to the other. We would also like to conduct inference using our estimator. That is, we would like to have methods, or our estimation method should facilitate calculation of confidence intervals or test statistics or whatnot. For this reason, we look at a third criterion, which states that the estimator should ideally have a known type of distribution, possibly asymptotic distribution. And this distribution should be approximable in some sense. That is, even if it's not known, we should be able to approximate it. In this course, we'll almost without exception only encounter estimators which are root and asymptotically normal. So we know their family of distributions, and all we need to know in order to pin down their distributions is their variance. Hence, this criterion tells us that we must be able to come up with methods for consistently estimating the asymptotic variance. But we could have multiple M-estimators which are root and asymptotically normal, and for which we could construct consistent asymptotic variance estimators. Hence, a fourth criterion may be in play, and that is the criterion of efficiency, again, possibly understood in an asymptotic sense. The efficiency criterion tells us that ideally, we would choose an estimator such that the variance, possibly in an asymptotic sense, is as small as possible. This again goes back to our desire to obtain as precise estimates as possible. A fifth criterion states that ideally our estimator should be robust to misspecification of various kinds. This criterion goes back to the concern that, well, our model may or may not be right, or it may be off, and therefore it would be nice if we could do inference even if our model is misspecified. Now, there's a clear trade-off here between having robustness to misspecification and having an efficient estimator. As we've previously illustrated in the case where an assumption of homoscedasticity leads to efficiency, while we may still obtain a consistent variance estimator allowing for heteroscedasticity, but in the process giving up efficiency. The sixth criterion states that ideally our estimators should not only have good asymptotic properties, but also good properties in small sample. You've previously encountered estimators which, under some assumptions, were unbiased, as well as had a small finite sample variance. These criteria are rarely in play in this course, where it may simply not be possible to analyze the unbiasedness or quantify the variance for the estimator. Especially in our nonlinear estimation framework, we don't even have the estimator available in closed form, and calculating its mean, as needed for investigating unbiasedness, is not really an option. The last criterion here is somewhat heuristic, but the estimation method should be easy to use. If a method is incredibly complicated and you have to be an expert in order to even implement it, then it's simply not going to be popular. Now, all of these criteria you may consider in exercises. And some of these criteria are topics to be investigated using theory, while others are more relevant using simulations. And I encourage you guys to think about these criteria whenever you encounter competing estimation methods in practice. So this concludes our lecture on inference within the M-estimation framework. Next, we'll take up the topic of maximum likelihood estimation.